Yes, I can hear you.
Ed, can you hear us?
I can hear you. Yes.
Okay, great. So what motivates this panel actually is the title is Key Technological Gaps for Broad DTN Adoption. And the idea was to collect very experienced people in the DTN domain and try to briefly pitch which is the topic they believe is what hindering like a broad DTN adoption at this moment. And I was pleased to find that actually Scott, Ed, and Rick actually are going to touch on different topics that are potential limits for such a broad adoption. So the idea now is each of the guys has prepared like a small 10-minute-ish speech about why they believe that interoperability, scalability, and reliability are the core limiting factors at the moment. So with that said, I guess we can start. And how about if we follow the order of the screen here? So then I pass the microphone to you, Rick, for 10 minutes, and you can share with us what's your thoughts.
Hello. So I promise not to take all of the 10 minutes because I feel that the point of a panel is to also have a bit of a Q&A and a bit of a discussion. So I chose the topic interoperability for two purposes. The first purpose was very much what I discussed yesterday in terms of bridging the IP world to the DTN world, bundle protocol world. And that aspect of interoperability, to kind of summarize what I was presenting yesterday, I consider to be absolutely vital for, and I will repeat, step one, reinvent the internet is not viable. So no matter how clever our protocols and our routing concepts and our technology for communicating across deep space distances, if we can't include it in what everyone else is doing, where applicable, then we're actually wasting our own time. I mean, I'm sure we're, paying for our employment, but I think that we should also keep in the back of our minds that we're trying to do this for, and this is going to sound grandiose, for the good of humanity. We kind of, I don't know about you guys, but I got into the kind of the space ecosystem because I think it's something really cool and it's something that we should all collectively be looking to do. There's great science, there's everything that NASA and ESA and the other space agencies promote. Great for STEM, great for introducing children and all that kind of good stuff. And that means what we build has to work with everything else. When the first boots land back on the moon, whatever nationality they may be, and I will make no comment on that, I want to make sure that school kids can see it on a screen that their teacher presents on the slightly dodgy overhead system laptop that the school with a very limited budget has managed to afford, wherever that may be, because that's the reality. They're not going to be sat in Darmstadt or Huntsville watching this stuff. It's got to be able to go out to the public so people can watch it. And that means there's got to be that technological interoperability. That doesn't mean making Zoom calls to astronauts. That's a step too far. There are other aspects. But we've got to make sure that what we have so successfully built as the internet needs to extend out into space so that, 100 years' time, when we're all bouncing around in space stations in a sort of Star Trek world, that is still part of the seamless communication infrastructure that humans have built. Second aspect of that same topic is from a commercial exploitation. So we're already seeing an evolution in the way that space programs are funded, the commercial sector, and I work for a private company. The commercial sector is now very much being asked to do the heavy lifting, and particularly to exploit. Asteroid mining is always seen as the multi-billion-dollar thing that will save the space economy and turn it into profit. I don't know. It's a great thing to bandy around and raise funding. But commercial programs supported by governments are actively being tasked to deliver things. And they are coming to this from their background of assembling space platforms for LEO and MEO and communication companies and that kind of thing, and saying, what is this bundle? We know nothing about this. We've read some RFCs, we've read some CCSDS colored books. We've read some papers, but what was wrong with the internet? And so there's a bit of evangelism there as well, which I'm trying to, well, Vince actually did a great kickoff of that. And I think that's evangelism that we should all have when talking to commercial companies, because I know they are all reaching out to you, and if they haven't yet, they will do, because it's picking up, who say, you seem to know about this bundle protocol. What was wrong with IP? Does this work with what I understand? My network guys don't get it. And we've got to make sure that not only do we have a consistent message for them, but we actually have the technology which works as well. And that was part of what I was presenting yesterday. The flip side of that is that we can reuse what exists already. We don't have to invent everything from scratch. People have spent 50 years building the internet. Jeremy had that great slide showing the scale of the internet in 1971 or whatever, which was before I was born, I would like to point out, and where it is now, which is unmappable. You know, let's not discard the geniuses that have developed the protocols that worked, and the geniuses who developed the protocols which didn't work as well. You know, a lot of sort of Darwinian evolution has happened with protocols, and I think we can't live in a little echo chamber where we talk about deep space, no matter how fun that is. We have to understand that other people have considered networking and routing and what works with management and what doesn't work with management, how operations work. And I'm starting to repeat what Jeremy is proposing as well. So I'm in rough agreement with all of that that's happening. The other part of interoperability, which I wanted to touch on, was the reason the internet works at scale, and the reason fundamentally that it's called the internet, is it is the connection of multiple discrete networks into a heterogeneous whole. It's not run, despite Google and Meta's ambitions, it is not owned and operated by a single supplier. It is a rough consensus-based association of people who connect their systems to other people's systems. And this, I'm sounding a bit like an IETF flag waver here, but no, I am, so I don't apologize that much. That is because there are standards, and the standards have enough detail to allow two entities, be them commercial entities or government agencies, and increasingly commercial because that's where the money is, to connect their systems together for the benefit of both and their customers, because that's how they raise revenue. It's always about delivering service to the customer, and no one can be arrogant enough to think that their system is the one and only true system and nobody else's system is valuable. At internet scales, when you're talking about the sheer amount of data, and in space, obviously you could draw, it's so expensive to get out of there. And no one is going to say, you only need to use company X's assets. We will deliver that. No one else needs to follow. It is always going to be collaborative. And in order to collaborate, that means there has to be clean, clear, and actually implementable, that's a word, interoperable specifications where people can say, oh, I reckon I can have a go at that at home. Or within a corporate environment, which is far more likely, I think we can commission a project to actually deliver that, and we can sign up to whatever ITT or RFP that's come down as part of some program to say, yes, tick, we do that. Yes, tick, we do that. And we can prove it. And we have implementations because we read the specs and they were well understood. And that means everyone can play well. And so that's the other aspect of interoperability. And that's pretty much all I'm sorry. I think I could go on at length about this, but I'll be really honest.
That's right. Thanks a lot. Well, maybe we pass the talking to Scott. You have slides, right? So you prefer to keep it?
I think some things that Rick was saying.
Please.
I love this. Yes.
Raise some thoughts that I thought maybe I would make something up on the spot.
But you're going to change your topic, which is scalability.
No,
that's written on the slide.
It's still scalability.
Okay.
It's precisely in the context of what Rick was saying that I think I'd like to sort of extend the concept of scalability a little bit beyond what was in my slide. My original thinking was, what happens if the DTN actually takes off? And to our collective surprise, people like to start using it. and start using it in a broad and productive way, how do we support that? Because there are, as we've explored, there are processing loads on things like raw computation that are computationally intractable. That if you do pretty much any of the route computation things that we talked about, and if you are trying to extend that to 1,000 nodes, 10,000 nodes, or 10 million nodes, that as is, they don't extend. And so there's a concept of segmenting the network that is, as people have pointed out, is kind of directly lifted from the internet concept of autonomous system, but that has been shown to work very well and is part of the scalability that came up in earlier conversations here, right? The reason that BGP scales as well as it does is that there are autonomous systems, and forwarding through autonomous systems in a sequence, in a chain, in a tree, is a way of conveying information throughout the network that actually works and scales kind of indefinitely. The regions concept that we've explored a little bit in earlier stints, I think, and comes up every so often, and that I wrote a whole bunch of slides about, is a DTN based approach to doing the same thing. The idea being the same sort of thing that Rick has described as administrative domain, where you have you segment the network into manageable chunks within which routes can be computed, and beyond that, within which management can be retained and limited to an organization that manages some such nodes. There's an administrative scalability here as well as a topological scalability. How do you enable large numbers of network operators to interoperate? I think the answer to some extent may be the same sort of thing, a region / administrative domain / autonomous system concept where there's the segmentation of the network and connectivity among the segments. I have slides that I'm happy to talk about ways of doing that. I've got new ideas on how to do that, but then we can talk about that later. But I would extend that concept just a little bit further and say that the scalability that I think we need to support here is not only topological and not only administrative, it's also there's a security aspect to that scalability. That is, the administrative domain concept constitutes a gathering of nodes, probably under the administration of a single entity, and that entity, that administrative entity, may or may not want to share the details of connectivity among the nodes in that administrative domain. And the administrative domain then forms a security boundary, as well as an administrative boundary, as well as a topological and forwarding and route computation unit that I think ends up being indispensable to the growth of the network in the long term and a precondition to real scalability of the electronic network.
Thank you very much, guys. Super interesting. Ed, we can pass you the token and we can hear you.
Well, can you hear me?
Yes, I'm going to mute here just to avoid any loops. And go ahead. The floor is yours.
Okay. I did have some slides, but we don't need slides. I think conversational works well as well. I wanted to talk a little bit about reliability. The observation, as Rick was mentioning, as people start looking at DTN and saying, "Oh, DTN is a thing. It is becoming more real. Let's talk about it. Why doesn't the internet work the way we want it to work everywhere we want it to work? And what are the things that make DTN unique?" One of the obvious answers to that for DTN is the bundle protocol and the inclusion of a bundling layer in the DTN architecture. And one of the selling points, if you will, of a bundling layer is that we can do store and forward through a network, and that store and forward is meant to give us some level of reliability. And the idea that we can put data into a network and store it in a layer, a bundling layer, is unique, it's novel, and it opens us up to different kinds of things, like how we might secure data at rest, not just while it is in transit in the network. But it leads to other questions, such as how much reliability do we really get by looking at that storage? And how do we reliably manage the storage? And does that mean that before a piece of data is delivered to its destination, that I, the source, might be able to get rid of it sooner rather than later? And it allows us to have a concept of networking reliability that's a little different than we see on the internet. And for example, if we talk about a network being reliable, we will say things like the network is resilient, meaning that it is able to operate in increasingly off-nominal conditions. And if we have store and forward, then we have more resiliency in the network, because if a path does not exist, we can tolerate that and wait a bit until a future link comes on board. So we have increased reliability by increasing, in some cases, resiliency. We can talk about network availability and say that reliable networks are often available for data exchange. But if we know that the source and destination might not always be online at one time, we can say that the network, the DTN, could be available if the first hop into the network is available. So the entire thing doesn't have to exist, but we can assume that our access to the network is easier in a way because we can just get to that first hop. And then lastly, if we talk about the durability of data, that we don't lose data, we have such a rich ecosystem in DTN of how we would tag metadata into the bundle layer and the bundle PDUs, and how we would secure it and increase that security to include data at rest, that the durability of the data in terms of resistance to corruption and to maintain its confidentiality is also there, plus the general store and forward pieces. So when we talk about the idea of a bundling layer and the reliability of the network, DTN in its principal components, the ability to address time variant networks, and the ability to do store and forward data exchange, and the clever bits of adding secondary headers and extension blocks, as well as security components, all of those provide these fundamental technological concepts that can increase the reliability of a network, certainly when you're dealing with long signal propagation delays, but also when you're dealing with very frequent disruptions. And disruptions here certainly can mean a link does not exist, or we're having trouble with a link, or a link is lossy. It could also mean we just don't want to use a link for any reason. Maybe it's very expensive. Maybe the data rates are very low, and we'll wait for a higher reliability or higher data rate link at a different point. If we then say that there are fundamental building blocks inside of DTN that allow us to build a bundle layer that increases the overall reliability of the network through resiliency, through availability, through durability, then we have to ask ourselves the question that that's extra features, but it's also extra implementation and extra configuration and extra operation. Does all data need the same level of reliability? Does all of that reliability have to come solely from the bundle layer? And how do we talk about the different kinds of reliability and processing and storage associated with it on a case-by-case basis? And something that we are trying to understand in the DTN community at large, right, of which we are all part, is how do we talk about levels of reliability, the necessary resources to put against reliability, and to know we don't treat all data the same. In terrestrial networks, a way that we differentiate data is by looking at service level agreements or service agreements. Someone's data is higher priority than someone else's data, as the very, very common example. Service agreements don't just need to be defined under the auspices of differentiated services, transmit queues, who gets filtered. You can also add additional services such as how secure must the data be, or how much reliability and reliability features need to be associated with the data. Something that APL at large, we are proposing is that there's an ability to define classes of reliability for data, particularly as they would be implemented at the bundle layer, to say that there might be a low class of reliability for data, such as best effort, no storage, send it as best you can. If it drops, it drops. It's perhaps 1 hertz telemetry data or very small, constantly repeating data, and we don't want to have a lot of storage used for that. Alternatively, we could postulate a second class of reliability. We call it class 1 reliability, which would be basic store and forward. Without anything else added to a system, a fundamental property of Bundle Protocol version 7, RFC 9171, and also all of the versions that have come before, is that a bundle, as it moves through the network, can be stored and forwarded, which means that if it gets to a particular node in a network, it might waiting for the next link to be available. That is a kind of reliability. It's one of the reasons why we want the bundle layer to begin with, is that we don't just want to drop data if a link is coming within a reasonable time frame in the future, reasonable defined by the life of that data. And so that basic level of reliability is if we happen to have storage and it happens to be available based on some queuing policies or by priority, we are happy to hold on to that data waiting for the next contact. You can then build on top of that and say, then there are additional layers of reliability. We define a class 2 reliability that says we additionally would like custodians. And a custodian is a pretty overloaded term, which goes back to some early work in CFTP and Mars relay networks and so on. But there might be an idea where a bundle agent could say, I'm willing to hold on to a bundle, class 1 reliability, until the next link or the next contact is up, at which point I'll transmit it and forget it. I've held on to it until I can forward it. And once I have forwarded it, I wash my hands of this and I hope it gets on its way. It would be nice if there were certain nodes in a network that would say, for a particular class of data, for a particular type of user, perhaps a user who is really paying for the privilege, I will hold on to the data, I will transmit it, forward it at the next contact, and I will hold on to it until I know that it has gotten further into the network, either that it has been delivered or it has at least gotten to another like-minded node who will take more responsibility. And that responsibility of transmit but hold in case I need to retransmit is the kind of custodial behaviors that we're trying to define. And then we postulate additional classes of service beyond that, such as before one would delete their own data, instead of saying there is at least one custodian out in the network that has agreed to take the data, we might need 2 or more. And a lot of those advanced reliability cases talk to when might a platform choose to delete data before it has been delivered, but it has gotten into the network, that idea of availability. As we take a step back, one of the things that we see, and something that I spoke at the very beginning about, is DTN and bundle protocol and the bundle layers have the individual technologies necessary to implement these things in a variety of ways. There is probably not a single way to achieve these classes of reliability. Rick mentioned earlier that so much of our space networking aspirations now are being looked at from industry that are building out these networks. And there are some very, very clever people who are looking at ways of building not just standards-based networks, but standards-based networks that allow for invention and allow for clever differentiation of their services and how efficient they can be. I think that if we reimagine DTN reliability as the ability to support reliable classes of service and define behaviors, but allow individual networks and network owners and network operators to be clever in their mechanism as to how they meet those behaviors, then we have both incentivized private industry to say there's a way that we can be rewarded for our cleverness and save the standardization for how we might signal that across administrative domains and how we might have users request the class of service, but otherwise let the implementation be to the implementers. And those are my thoughts on reliability. I'm happy to answer any questions.
Thank you very much, Ed. Yeah.
All right. So thank you again for the nice work. Thank you, Rick. Thank you, Scott. I'm happy to open the mic for also the audience if there is any comment or any questions that you would like to ask. Also, I'm meaning also the audience connected remotely. Do we have any comments or questions for the panelists?
One, can I just come back on those?
Yes. So let's do something. I leave you three interact first, and then we pass the word for. We start with the questions from the audience?
Yeah, let's do that.
Thanks for the presentation. So I have a question for Rick. I would like to hear your take on the work that has been done at the ITF, the TikTok working group.
Yeah.
So more than interoperability, what they're proposing is just to go straight with an IP stack and then tweak some of the timers and adjust the queue so that we can support store carrying forward and so on. So how would that with that proposal of reusing IP with something that was before kind of discarded and now is coming back?
Is there enough? We need the mic back.
Here I go.
Thank you very much. So yes, very happy to try and answer that. First off, personal opinion. Secondly, the reason I say that is, unfortunately, the IETF is one of the most political, non-political organizations out there. There was a little bit of politics involved, which made the whole, just a little, that made the whole thing a bit messy. However, I actually completely appreciate why TikTok came into being, and I still think it has some value, and I'll qualify that. TikTok came into being because I believe, as I said 5 minutes ago, I think there was a general misunderstanding and a frustration with what on earth this DTN technology was and what this bundle protocol was. And it sounded a lot like we were reinventing the internet. And a lot of people went, hold on. This seems mad. And people said, IP is an unreliable system. IP packets move from switch to router to switch to router across the internet in a sort of hop by hop way. IP is cheap. You buy a switch or a router from Cisco, not a lot. Buy one from Temu, it's really cheap. Why can't we just use that? Why can't we save some cost here and just use IP? It seems so much simpler. That made quite a compelling argument to some people that perhaps we should have a look at whether IP has changed significantly. The advent of Quick was a really interesting sort of tipping point in the conversation. Quick is a very, very clever protocol. Does some very cool stuff. And it was a fair question to say, can we look at Quick? And does it perhaps address some of the problems that TCP IP had that caused sort of the birth of the DTN thought experiment that's now become live. I believe, and in fact it's more than belief, I have seen proof that TCP/IP and its congestion control approach to handle congestion on the public internet, which is based on sliding windows, timers, and backoff route packet control, is the same congestion technique that is being used for QUIC and does not work over the long delays that we see in space. Carlo Caini's team at the University of Bologna have.
He's online.
He's online. Carlo presented at CCSTS some very good, proper science with data to demonstrate that it just does not work, which is fantastic. So we can put that to bed. However, the exercise around the tip-top concept of what of the IP world can we reuse, I think is a very strong idea. Marc Blanchet, who was one of the people originally saying perhaps we could just use QUIC instead of BP, which I disagree with, has also proposed how we make DNS work in a solar system. And that proposal is really strong, and I thoroughly support his work on that, and I think that has legs. And that's the kind of thing that the tip-top group can do really well. They can include the traditional internet group of the IETFers and say, we have some space problems. What can we reuse and what do we have to say, doesn't work? That has real value, and therefore I support it. Does that help? You want to say something?
Actually, I think that's a really, really good answer. So I endorse everything you said. I have looked at and compiled a list for me that works for me of things about the way the internet is structured and operates that are incompatible with not so much long signal propagation delays, although that as well, but in particular punctuated connectivity.
Yeah.
It's just there are all kinds of things that the internet is based on that do not work when we have connectivity that has these limitations. This is not to say that the bundle protocol is the only way you could solve these problems. It is a way that has been developed and shown to work. Is it the only possible way to do it? Nope. There's a lot of software that can be written. So if somebody wanted to write something else, and say that this is not part of the internet protocol stack, given the resources, one could do that. I don't think that's desirable. I don't think it's necessary. I think what we have is quite good, but my voice is not the only voice.
Thank you very much, guys. We have Felix Flenger from ISA with their hand prize over there. So Felix, please go ahead, take the mic, and if there is any loop with the audio, ping me. I will mute here very quickly.
Yeah. So I mean, let me be a little bit provocative.
Felix, can you want to go ahead?
Do you hear me?
We are not getting audio from you, and I guess.
Try again. Now it should work.
Yeah. Here we go.
Okay, great. So let me be a little bit provocative to make it more interesting. Yes. Obviously, to address what's all very interesting, all very relevant. Who would argue that we don't need scalability, interoperability with internet? I get it. Reliability, you cannot argue with that. But we should not think that once we have solved these problems and we have good ideas how to solve these problems, that we will see large-scale adoption. So up to now, we don't have hardly any small-scale adoption today. So this is, I think, the real issue. Of course, we have ISS payload DTN service working very well. We have the PACE missions, where I really would like to get some experience from that mission. Haven't heard anything yet, but that's about it. Yeah, we have Moonlight, which we had to make into using BPv7. Yeah, we will still need to see how much BPv7 we really will have inside the network. I think it's very similar for NASA Elcons. Yeah, it's also kind of external requirement onto that. So I think the main problem is really how can we stimulate small-scale adoption, which would also allow us to get the experience to address the larger problems. I'm not saying we should not look into this, we should not have research into that, but it's something, for me, it's really a process. We have to start small, we have to show benefits in small-scale adoptions of that, which might be not really internet working scenarios, but we really need to prove that we can solve specific problems, that we can solve these problems in a better way than we address these problems today, because otherwise no mission will go for adoption of these technologies. And I think this is a question to actually all of you. How can we achieve that, and how can we kind of start really rolling out technologies? I'm not aware of any NASA mission confirming phase C or something confirming to go to bundle protocol. So how do we get to the point that space missions per default say, of course I'm taking bundle protocol. Like today, of course I'm using, I don't know, TM AOS frame. So I think that's the first step, and we have somehow to go in this direction to enable this. It's in the end, it's an evolution. Internet was not kind of top-down designed and we have all these problems in the future. Now let's solve it. No, it kind of created from a specific problem of kind of connecting 3 different networks. So I would like to go a little bit back, and maybe you have some ideas. How can we promote the small scale adoption?
So I have 2 things to offer on this. One is a perspective coming from JPL and doing several for several years there. Spaceflight mission operators are risk averse. They are risk averse because their missions are extremely expensive, extremely visible to the public. When they fail, they make a lot of news and they endanger a lot of careers. So there is very low tolerance for doing anything that that is new on a spaceflight mission that doesn't save enormous amounts of money or provide some other extremely significant benefit. It took the failure of an antenna opening on the Jupiter mission, the name of which I forget, to introduce the validity of data compression on transmission of telemetry and science data from space. Until they had to do it, nobody was willing to send compressed data from spacecraft. That kind of thing we can't expect necessarily to happen in contemporary spaceflight operations. We have to some extent, we have to just press forward with whatever inexpensive missions that are willing to take on the protocol and the DTN architecture and go with it because they're able to tolerate the risk of doing something new, and there has to be some compelling reason for them to take that risk. The second perspective I would offer on this is that as we have observed from time to time, there are applications in terrestrial networking for which DTN is actually quite a good fit. There are particularly network connectivity to underserved parts of the planet. We are aware of these things. I was at a conference a couple of weeks ago where this was discussed at some length. That there are deployment opportunities in underserved elements of humanity. Something about like almost 3 billion people don't have any internet access. Well, we can try to serve access to those people, and it's much less expensive, much less visible, much easier to do. You don't have to launch a giant, explosive device into orbit to make it happen. And I think that's the other avenue that is open to us for expanding awareness of DTN and awareness of the benefits.
Ed, do you want to respond before me?
No, go ahead. You have the mic, and then I'll go third.
Okay. So very quickly, Felix, I think you're doing it right. So, I just want to sort of name check you here. I think you're doing a fantastic job in your role at ESA. Given the move towards more commercial and industry partnerships on programs, the role of the space agencies to say, this is the core capability you must have in order to deliver this. We are the technical experts who are setting the requirements for these missions. In that position, we're starting to see over the last 18 months, and it's accelerating, that ESA and NASA as well are saying, it would be great to have DTN capability. If you want to differentiate yourself from other people bidding for this, then DTN would be one of those things we would like to have. Don't make it, to address Scott's point, don't make it the critical part of your communication infrastructure, because we are risk averse and we're talking about the moon or nearby, so that direct line of sight, real-time communication circuits and that kind of stuff is still entirely viable. But the message coming from the space agencies, and driven by CCSDS and all who sail in that, to say, we think that the evidence we're seeing from the small-scale CubeSat operations and the test beds and the simulations, we think Beacon V7 and DTN as a whole has legs. Please include it so that we can start to now try it at scale. And I think that gives the space agencies, who are no longer funded to such an extent that they were in the 70s and the 60s to run these, Apollo-style programs, their new role is the technical governor and the technical oversight on these programs. Their ability, and Felix, you are doing this, to say, DTN looks incredibly promising, please get it into these RFPs or whatever. That's how it happens as far as I can tell. But I am actually not the expert in this area. Ed, go ahead.
No, but excellent comments, both Rick and Scott. I want to add a couple of quick observations myself. Number one, when we talk about adoption ever in space, there will never be, never say never, is unlikely to be, billions of things out there in our solar system in our lifetime. Success to me is relative adoption, not absolute adoption. And one of the economies of scale that we talk through are yes, internet devices are relatively inexpensive on the terrestrial internet because a router at a store costs $30 or $100, but a router in space costs, $5 million or something like that. There is fewer things, but it's a harsher environment. And so when you start talking to companies, then you sell orders of magnitude fewer at orders of magnitude higher value. And so there are likely cases to be made for vendors to value this. And so relative adoption, 30, 40, 50% of the hundreds, not thousands or hundreds of thousands of missions adopting and putting these kits together actually can get to the point where it's motivating beyond just the space agencies. The second observation, opinions only, of course. The second observation is we have a sense as part of the networking, as networking nerds and people that tinker, to say, well, if you want this capability, go download it. And go download it from somewhere, go buy some Raspberry Pis or Arduinos and figure out how to slot it into your various systems. And that is motivating for a group of us, like everyone here. But if you're on the hook to put this into an operational system, that actually makes you take a step back and say, very interesting. It doesn't feel real because I can't buy a nice shrink-wrapped box just yet. So someone hasn't put all of their coins behind this, and I don't want to do it myself. And I think trying to figure out that story, not download something and tinker and put it into your system and it's on you to make it all work, is an important thing to get past. And really, to me, is the thing that will show maturity. The last, well, I had two, but I know I'm taking a little bit of time here. The last is reliability and resiliency is something that we're going to struggle with even at scale near Earth, where you will see tens of thousands and more spacecraft. And those systems are fragile, and we know they are fragile. And as we try and understand how we increase reliability, there is probably a good story to be told there related to just resiliency in the network, which is, I think, not fully explored. And then the last thing, and I'll be quiet, is applications. As we start building up applications near Earth and in cislunar and in Mars, and generally in the flight software communities driving space companies and space agencies to say, here's an app that I would like to get out there. It just happens to use bundle because we need the bundle layer. That is very motivating. When people integrate systems on spacecraft and on landed assets, if they can purchase a solid state recorder, they don't want to build them themselves. Actually, I worked on New Horizons and we built our own solid state recorder. Don't do it. If they need a radio, they purchase the radio. They don't want to build it themselves. If they want payloads, science payloads, they don't want to build, in many cases, the science payloads. Tell me who makes them, and I'm happy to put them on the device. It's not that they don't want bundle. It's not that they would rather have IP. It's not that they are locked into CCSDS. It's that I don't have a place for someone to give me this new cool thing. I'd be happy to have it otherwise. And I think getting over that is the thing that will see the relative adoption of DTN in the space area.
Thank you, Ed. We have Scott Johnson in the queue. So Scott, feel free to unmute and speak up. We cannot hear you.
Hello?
Yeah, there you go.
Yeah, okay. I originally had a comment about interregional forwarding for Scott, but on the topic of accessibility of the network and growing the network into adoption, once upon a time, Bell Labs created this wonderful operating system for their phone switch, but they didn't really have enough engineers to populate all the switching centers and to program the thing. So they gave it away to all these universities, and we wind up with the entire lineage of Unix thereafter, which touches every part of our lives. To that end, we're trying in the IPN SIG to make a similar outreach approach into the university ecosystem with a network that we're calling the Bundle Bone. And I think in the United States, at least, where we're beginning the foundations of this, and then we can obviously spread it to Europe and other places. This can provide kind of the testing bed and the out-of-the-box experience that Ed was just speaking of to the educational community, where we can begin to build the kind of workforce that we're going to need to support a network at scale and provide the engineers necessary to all the space startups that are going to wish to include bundle. But my original point was, Scott, I kind of see IRF as a key component here to the network growth as a whole. It not only allows us to limit the scale of the contact plan, which is my actual question, how large can we make a particular region? But that ties in with the concept of an administrative domain being represented by a region. And then in what instances, what is the scale of the node numbers you would see as the limit for a single region? And is that beyond the scale of what you would perceive as to be within the range of an administrative domain of an organization?
A good question, and there is no immediate answer for it. There is, we're looking at a wide variety of ways of computing routes through the network topology. And we're still examining ways we can optimize that, and ways in which the volume of contacts in the contact plan can be managed by these different algorithms. How that can increase. If I were going to guess, I would guess that with what's currently in ION, for example, it's probably a bad idea to work with a contact plan that is more than, maybe a couple of hundred contacts, which might limit the number of nodes. That is to say, the nodes that are cited as the sources and destinations of data in these contacts to a couple dozen. And in that sense, you might be really ultimately, certainly hundreds, ultimately thousands of different independent contact plans, independent regions that are interconnected. Some of the ways we're talking about doing broad computation might expand that. You might be able to have 1,000 nodes in a region, and that might be perfectly doable. I think the research is continuing on that, and I think that the real answer is that ultimately it's going to have to emerge from operational experience and changes as the technology advances. A thing that I think is a concept that can make this easier is a mechanism for constructing a predefined grid of regions and plugging administrative domains into that grid, the elements of which are pre-numbered, so that you can, and as an administrative organization, you might say, I've got 70,000 nodes. Well, that means that you request 70,000 topologically adjacent regions and populate those regions with your nodes, and then the communication among the nodes within your administrative entity, among those 70,000 is relatively rapid because the regions are adjacent, but you can still communicate with nodes in far distant regions because the structure of the region numbering makes that straightforward. I think that's a powerful concept, and it enables the interregional forwarding to be implemented in a more effective way. I think one way or another, we are going to need that mechanism in order to extend to larger numbers of nodes. And the last thing I will say on this is that while the number of nodes in space may never be millions, the number of nodes that might be interested in the information coming from space could be in millions, because it could be people on Earth who want that data. And in that sense, the network that is delay tolerant, certainly at the space end, and arguably at the terrestrial end as well, for simplicity, could easily be millions of nodes. We need to be able to support that in case the network does grow in that way.
Just to add my 2 cents to this, I think you're absolutely right. As I said before, the subdivision of autonomous systems is a way to divide the problem into manageable chunks to allow various different organizations to collaborate and yet still maintain their own trust boundaries, their own administrative policies, and yet still play well with others. To address Scott Johnson's question, I think the underlying ambition is that the size of a region is irrelevant. What you exchange is effectively the circumference of the region. So you talk about the edges rather than the area of your region or the volume. That's another part of divide and conquer. Obviously, there's an assumption in there, which is you could say everything inside my region is addressable in some way. Now, of course, in the IP world, I'm sounding like a broken record, yeah, you have subnetting. So you can say, I own the subnet, my gateway into my subnet is X. Going to the question, what can we do to make DTN better. We have a slight hiccup with some of the way we do address it. Subnetting isn't that nice or natural. We don't have that nice little bit masking property that it comes to. We kind of forgot that bit. Brian Seacross and co-authors are doing a great job with the IPN EID patterns as a way to express that there are groups and stuff, and that's great, and it's going a long way. The allocator ID stuff in IPN was also so that you can make some administrative partitioning and assumption that if I've got a NASA IPN address, then I should probably get it to NASA. And that might be to one of the administrative regions or my nearest administrative region. Where I slightly disagree with you as the topological grid thing, I prefer more of a logical connectivity tree. So you might have some top level peering, you know, at the root of it, but NASA might have its own internal tree with its own subdomains within it that it decides how it's going to connect. I think prescribing some kind of spatial subdivision, it just, I don't know, but I'm willing to be proven wrong.
I want to discuss, but
Not now. And on a serious note, that might still be some of the problem. So we love this topic. Well, we love this topic. And we get excited about it, and we will point to the open questions. And I think we need to be a little bit careful when talking externally and when being observed by people who are putting down many dollars of euros on these programs to not say, oh, it's still a great experiment. Oh, that's still badly broken. We have got to a very serious tipping point now where proper money is being spent. And we must make sure that although some of it is still an open question, a vast amount of it is pretty stable. And we can give that message back to go back to Felix's question of how do we give it out. I think we all share some responsibility to put out the message that, sure, fragmentation, oops, but basically BPv7 works. For as far as we can test it, we have yet to fundamentally break it. So we are now ready to go with it. We're ready to launch it. We're ready to test it in anger. This isn't a thought experiment anymore. Even if there are things we're still arguing about. So say something sensible, please.
Well, it would be a first, but what I would say is we have to accept both that it works, the technologies work, they are ready, and we will learn more. A few years ago, I got to write this wonderful sentence that made me feel at my advancing age, which is the internet as it worked at the turn of the century is different than the way the internet works today. And of course, that is true. And we accept that there are new networking technologies now than there were 25 years ago. And we accept that the internet that will exist 25 years from now is likely going to be different than whatever we're doing terrestrially right now. At no time do we say, because the internet 20 years from now is likely going to operate differently, that whatever we have today isn't ready for operation. And I think we have to accept the same part in DTN. What we have today is ready for operation. And the DTNs that we have 25 years from now are going to be different than the DTNs that we're building today. And those two things can both be true at the same time. And we need to make sure as we engage externally that we are letting people understand that the fact that it's going to be different later does not mean that it is not ready now.
Pass the microphone to Alberto.
So I want to give one thought and then I have a question. We look at standards in the specifications, and I found some guys very interesting that reveals the nature of where we are today with DTN as a market, as a technology. Which is the following: when you go to, for example, PTPP, and I had the luxury to be a PTPP delegate for a couple of years when I was at Motorola, you would see both the vendor, the Ericsson's, Nokia, the Motorola's of the world, together with the service provider, the customer. And the vendor developed the technologies, the customer adopted, but also the customer vouched for this specific flavor of the technology so that they would create, some competitive advantage. When you go to IETF, which, IETF is much more open, which is great. But when you go to the mainstream technologies, you find some of the same, which is, a lot of the innovation is being driven by, the people making money with it because they have the resources, right? Not something against. When you look at CCSDS, it's slightly different because traditionally CCSDS has been an organization of the space agencies that have been developing their own technology because it is a niche and also because the business model of the space agencies have been by contract engineering services. I don't buy products necessarily. So what we find now is when you think about CCSDS and DTN, is that you have both the space agencies are both the vendor and the customers. Because if you look at this, most of the technologies that we use today have been developed by the space agencies. Good news that we're seeing, to your point, we are seeing now the first to more and more commercial companies that are building solutions, products in the areas. So what we're going to see over the next several years, the first argument companies develop is that you're going to see this change from people just specifying things because they look the right thing to do, to specifying things because they are really needed for the next products, the next feature, or because I have a patent and I want to, leverage my competitive advantage. So that's happening, but it's happening slowly, but it's happening. So we're gonna continue seeing that transition, which is great, great news. Now, my question: what is your view on mobility as both interoperability and most likely an scalability issue? And when I say mobility, is the fact that different than the internet in the space domain, everything moves. And there doesn't seem to be an elegant solution to solve for that.
We have a few more minutes, so feel free to take it.
Let me try for a quick answer. There's movement and there's movement, right? There's geographical movement, which is inevitable and dangerous about it. There's movement within the topology, and that you have some control of. That is, you can control which things are going to be and are currently in communication with other things, regardless of the geographical relation. That's kind of the basis for what we do in contact graph routing is that the nodes that are cited in the contacts may or may not be geographically adjacent, and yet they are topologically adjacent, and that's what makes the route computation work. So I think which is kind of an alien concept to the internet because geography and topology typically are pretty closely related. It's a conceptual leap that is important when we're talking to people about DTN and about the challenges in given with mobility. Which mobility is important talking about.
Everything he just said, but I think there's one extra form of mobility, which is our called administrative mobility. So that is where an asset moves from one organization to another organization. I'm not sure how often that would happen, but it is a form of motion. I think there are some very interesting things as we get into the region concept, where ad hoc adjacencies under emergency conditions and things like that will start to be behaviors that are demanded by the mission operators. And I think, to your point about the growth of industry, I completely agree. Both you and I are the next generation of small, vibrant commercial companies trying to punch into this. So it's great that you're here as well. There's the demands will be such as an ESA asset is next, not topologically, but physically close to a NASA asset, way out, past Neptune, and an emergency occurs, and a relay must be made. Can we now somehow form some adjacency across an administrative domain? That's at ESA, sure. What if it's Chinese asset? How does that work? And there are whole policy questions, which is a whole different form of mobility. Those, to take Ed's point, those are the things we'll have to fix next. The technology, I think we can say with confidence, yeah, it's ready, let's get it smashed. And I really like your point about currently we are offering capability to programs. Go down the CCSDS checklist, choose what looks good, let's build it, let's run it, and there'll be that evolution to where mission operators are saying, I need this capability. Do you have it? Do you not have it? And that's driven by their need rather than the guidance they're receiving from CCSDS. And we'll see that evolution, I will. And then we'll get into the how do we administrate this at a sort of globalish level. And I want to be retired.
And I don't know if you want to add something, otherwise we're closing to end the panel.
I was just jumping in to say, number one, I agree with everything. And actually, Rick, you made the points I was going to make about policy and security, of course. The last part of this is opportunistic, almost by definition means, who are you? And that could come from, I know who you are, but I don't expect you now, or who are you? And we need to be careful as we build networks to understand that just because we can does not always mean we should. And so understanding the policy pieces of this are hard on the terrestrial internet. We're certainly learning lessons in 3GPP systems. And this might be another area where DTN has a little bit of an advantage in its ability to mark data, in its ability to wait until we understand whether an opportunistic contact is a good contact or not. And as we talk again about resiliency and how we value add here, we'll figure it out over the next decades. But there are some very good building blocks here that can provide capabilities beyond what we can do otherwise without DTN. And we shouldn't lose sight of that as well.
All right, guys. This was amazing panel. So let's appreciate the participation of Scott, Rick, and Edwin.